All right, so we're going to start the second session of the morning, and here we're going to dive a little bit more into hardware stuff. So this is a workshop or a tutorial organized, co-located with ISCA, and I assume many of you are hardware people. So how many of you here work on custom hardware? Okay, great. So hopefully you'll get to learn something about this talk. So specifically, I'm very excited to talk about how we use TVM to compile models to the VTA Deep Learning Accelerator. And what this talk will cover is this VTA effort that we've had within our group, which is an Apache TVM open source deep learning accelerator. It's an accelerator that we ship with a compiler so you can run end-to-end models onto it. And I'm going to walk you through the accelerator design and discuss some compilation challenges that arise from hardware design decisions. And finally, I'm going to showcase how Relay and TVM convert whole deep learning, deep neural network workloads to run on VTA. And we're going to do this both in Colab on your laptops, where you're going to run essentially these hardware simulations, but also I'm going to do a demo on this FPGA board here. Unfortunately, that's not something you can do on your laptops because you need this device, but you'll see that we can essentially run a lot of things on either platforms. So many of you already know that there's this boom, this explosive growth of deep learning accelerator designs. We're seeing tech giants build their own hardware accelerators, as well as traditional IC vendors. But also we're seeing an explosion, a boom in hardware startups that are all designing their own hardware accelerator with a twist. And the challenge when you're a small startup or research group that's taping out silicon is that you have this huge abstraction gap between your hardware design and those high-level deep learning models that are specified in your favorite framework. And in fact, you have to build all these layers of the software stack in order to get something as simple as a ResNet to run on your hardware design. And it turns out this is actually a lot of engineering work. We're talking entire software teams dedicated to building these compilers for a hardware design. Why is it hard? Well, first of all, there's a lot of different deep learning front ends. There's also a lot of new models being introduced, as Jared pointed out, every day. And also, if you're designing hardware, this is part of a continuous process. There's going to be multiple iterations of hardware designs. You might also have high power or low power designs that you're constantly iterating, designing, and testing. And this means that essentially your compiler will have a lot of moving parts. And that can be a huge burden in terms of maintaining software. And when we build TVM, we believe that people shouldn't build ad hoc compilers unless they're a huge company that has the resources to do so. So we're going to look at how we can use TVM to hopefully reduce some of the pain of building a compiler for your hardware design. So we've already shown success at targeting CPUs and GPUs. I hope my colleagues have convinced you by now that there's a lot of value in using TVM. And this is mainly because you first of all have model translation to Relay from those high-level frameworks, but also Jared showed that you have this rich set of graph-level transformations, passes that you can implement yourself, things like quantization to target your special hardware device. And with TVM and auto TVM, as Eddie pointed out, you have this flexible and automated set of schedule optimizations that essentially give you performance portability on those different hardware backends. And what's nice is that you can also plug in your own code generation, like LVM, CUDA, Metal, etc., so you can target these hardware designs. But the question is, can you do the same for an accelerator? And of course, it's not just gonna, you're not gonna be able to just plug your accelerator and hope that TVM will compile down to your design. So we're gonna show you how we did this for our VTA accelerator. But before we do that, we need to understand why accelerators are different beasts than CPUs and GPUs. Of course, the memory subsystems is going to look very different, right? We're used to implicitly managed caches, but in accelerators you have scratch pads, you have stream FIFOs, etc., and this is all explicitly managed by your software stack. You also have new tensorization primitives that perform essentially computation on multi-dimensional registers. And also, you'll see more exotic data types, like very narrow integers, or perhaps non-traditional IEEE 754 floating point types that you don't find support for in your CPU or GPU yet. But also in terms of ISA, accelerators essentially describe these high-level, many-cycle tensor operations, like loading a huge tensor from memory into SRAM, things like conv2d over huge amounts of data that are specified by a single instruction. And finally, more subtle aspects of hardware design, like for instance, how do you utilize your memory pipeline and compute resources synchronously at the same time? And in CPUs, you don't really have to think about it because it's essentially a self-driving machine. You can do cache prefetching, you have simultaneous multi-threading to utilize all these resources at the same time. But in hardware, you need a bit more of an explicit push by the software to synchronize your resources. For instance, we've seen that TPUs use decoupled execute. So in order to study these challenges and the differences between CPUs and accelerators, we built a deep learning accelerator in-house. This is an open source deep learning accelerator. When we started this project 2 years ago, there weren't a lot of open source designs out there that shipped with a compiler. So we wanted to build it from the ground up. And really, we wanted to see what it meant to augment TVM and relay to support deep learning accelerators. And so we started with an initial version, which has been specified in Vivado HLS to target Xilinx FPGAs. This was our version 1. It's easy to prototype hardware on FPGAs with HLS. But actually, we're shifting over Chisel, which is going to be our long-term design that is more modular, more scalable, composable, and portable. And we're very excited about this. Our colleague here, Luis Vega, has done heroic work redesigning from the ground up Vita in Chisel. So this is super exciting. So if you look at the TVM and Vita stack, Tianxi already introduced the Vita accelerator design. And we're planning on targeting not only edge FPGAs, which I'm going to demo today, but also let folks program hardware in the cloud. And we're also working on taping out and targeting ASICs in the near future. And if you look at the layers of the stack, there's a pretty big abstraction gap from your TVM IR down to something like an FPGA. So you need to build abstraction layers. So we have a Vita microarchitecture. You can think of it as a programmable accelerator template. There's a ISA specification that specifies a contract between hardware and software. And then we have this runtime and JIT compiler that essentially handles code generation from the TVM layer down to our custom ISA. And of course, testing in hardware can be cumbersome. So we actually have a simulation infrastructure. And this is what you're going to use today on your laptops so that you don't need an FPGA to run our compilation examples. And this is really nice because you can do fast simulation. You can test compiler passes. When you're a compiler person, you don't want to deal with FPGAs when you're on the train or the airplane or at the coffee shop. But also, we have this really exciting thing called TSIM, which Luis is going to talk about. And this does cycle-accurate simulation with Verilator from TVM, which is really exciting for us architects. And finally, FPGAs, which I'm going to showcase today in parallel with our Colab tutorials. So the goals of Vita is to build this research blueprint for a complete deep learning acceleration stack. And that's something that we're very excited about because that lets us do experimentation across the stack. So we're not just hacking software, we're not just hacking hardware, but we're doing both at the same time. And I think that's very valuable to people like architects who want to investigate one research idea and have already a deployable stack that they can test on an FPGA. And finally, this is open source. It's under Apache governance model. So we want to have a really strong and thriving community. I recognize some people here who have already pushed PRs to Vita, and I'm very grateful for people who are contributing to the effort. So I'm going to jump onto a more technical, I'm going to shift gears to a more technical talk now. And we're going to do our hardware architecture deep dive. And I promise it's not going to be too painful. And we're actually going to start with a very simple example of a CPU. But before I do that, I want to reiterate that Vita, behind designing Vita, we wanted to build very simple hardware and basically offload all of the complexity of managing hardware resources, of synchronizing tasks to the software stack. Because we have a very powerful software stack, and essentially we don't want hardware that is self-driving. We want essentially hardware that is minimal and simple so we can get the software to schedule it in the best way we can And I'll give you more detail about this. So let's start with a very simple example of an ALU connected to a register file. This is something we're all familiar with from our undergrad classes. And most CPUs, they perform scalar operations over a single data element. You might also have vector processors that perform SIMD computation over a vector of data. But now this new notion of tensor processors essentially perform operations on multi-dimensional tensors. So we're talking about tensors of rank where your rank is greater or equal than 2. And although you might think of it as a similar SIMD style programming as you have with vector processors, it's actually quite different because it requires different constraints in terms of memory layout, for instance, and operation ordering. So if you look at how a typical matrix is stored in row major order in memory, it's pretty straightforward. Each row is stored contiguously like this. But if you have to feed this array to a tensor processor, you have to reorganize your data layout so you can actually feed your data in these 2x2 chunks, for instance, in this example. And that requires a different memory organization. And as you can see, these blocks that I've highlighted map to 2x2 tiles in your array. So that requires memory transformations from the start. This is the first challenge to target tensor ALUs. So we're going to build up our design. Of course, it needs to be controlled by a series of instructions. And for our VTA design, we utilize micro ops, which are essentially RISC-style instructions. You're familiar with these kind of ISAs, where you essentially perform element-wise operations. But instead of registers, we're looking at entire matrices that we can perform these operations over. And for deep learning, we want to do more interesting things than just element-wise computation. We want to do dense linear algebra. So we're going to drop in a GEM core. GEM stands for general matrix multiplication. And that lets you take multiple tensors, multiply them, and add them to another tensor. And this is essentially the building block of dense convolutional neural nets, but a lot of other neural networks, it turns out. And if you look at matrix multiplication, you've probably looked at this before. You're multiplying two matrices together, but the key takeaway here is that these matrices A, B, and C in deep learning could have different shapes, but they could also have different data types. So we're going to specialize essentially the memories that feed those matrices into our GEM core. So if we wanted to introduce a new instruction that does dense matrix multiplication to our ISA, something that would look like this. You take register 1, and then you add the matrix multiply product between an activation and a weight matrix, which is what you see in most convolutions and dense operations. Then you're going to need essentially to update the values in your register file. That might be a 32-bit accumulation. But you also want to read from an activation and weight buffer. And this could be different data types, right? We could have a narrow 8-bit activation and a narrow 4-bit weight. So we're going to have these specialized memories to feed data into the GEM core and update our accumulation values in the register file. So far, so good. We obviously need to talk to the outside world. So we're going to have DMA engines that are going to load data into these buffers and in and out of our register file. So we can do essentially computation as we're moving data in and out. And in order to orchestrate all those functional elements, we're going to have this task dispatcher. And the idea is that this dispatcher will send multi-cycle tasks to our 4 different functional units, our GEM core, our ALU, load and store DMA engines. And these are going to form our 4 high-level task instructions. And actually, there's a lot of parallels with the TPU instruction set architecture that is described in the paper. And I assume that a lot of deep learning architectures use a similar high-level programming model. But here's where things get interesting. For instance, if you want to do dense matrix multiplication, there's a lot of different operations that you could do in a neural network. And what's nice about this high-level task instruction is that it calls into our micro-up buffer. Our micro-up buffer, remember, contains those RISC-style instructions. And we can essentially describe a microkernel that performs different types of operations in your neural network. And we're talking about different operators like conv2d, group conv2d, conv2d transpose, dense, but also they might have different shapes. striding access patterns, etc. And what this allows us to do is essentially get software-defined flexibility. So we're hardening the hardware, but then we can define different types of operators in software, and that lets us do different types of workloads from generative neural networks to more classical vision classification models. We also have ALU for less dense operations, things like ReLU, bias add, batch norm that you have in a lot of those vision models. And then finally, we have our memory DMA operations like load and store that do bulk memory transfer to and from DRAM and SRAM. Now we're going to talk about something that is a little more subtle, but how do you schedule those tasks? So we have this task dispatcher, and a naive way to schedule those tasks is to perform one operation at a time, right? You're going to do a load operation, then you're going to do a matrix multiply operation, and you're going to essentially alternate between those. But essentially over time, you're underutilizing your resources. So you like to essentially schedule them in a way that you utilize resources concurrently, a little bit like this, where you essentially have a pipeline of tasks. So that means that as I'm performing data transfer operations, I'm also performing computation. And in order to do this, we essentially have to shuffle or design around to essentially define this, this pipeline. And what are we going to do here? And as you can see, by the way, we can actually save quite a bit on latency because essentially by reorganizing these tasks in a way that makes them execute concurrently, we're reducing the amount of time we wait for data, and we're effectively hiding memory access latency, and this is giving us a lot of savings in terms of execution. So in order to support such an execution model, we need to re-architect our design, and we're going to start to organize it into modules. So we're going to have a compute module that takes care of doing the dense computation and the ALU operation. We're going to have a load module that loads data from DRAM to SRAM, and also we're going to introduce an output buffer so we can store data to DRAM concurrently as we're loading that output buffer as we're doing computation. And as you can see now, we have essentially this task pipeline from load to compute to storing data. And these pipeline stages, they communicate over these unidirectional memory channels, like your activation buffer, your wait buffer, and your output buffer. And when you look back at this pipeline diagram, if we want to guarantee timely and correct execution of our task, we need to enforce some form of dependency between these tasks. And we categorize them in true and false dependencies. If you remember your computer architecture textbook, it's read after write and write after read dependencies. In order to enforce these dependencies between tasks, we actually use hardware FIFOs that essentially connect a consumer to a producer or vice versa. And the idea is that when a module is done producing data, it will push a token that the consumer can then pop when that token appears to signal that the data is ready to be consumed. And so we use these FIFOs to signal between modules that data is ready to be consumed or data is ready to be overwritten in the case of a false dependence. If you look at these tasks, we can introduce read after write dependencies between load and matrix multiply operations, which makes sense. You want to perform computation once your data has been loaded into these buffers. And that will be communicated via a queue between the load module and the compute module. You can do the same between the compute module and the store module. But of course, you need some form of handling back pressure. So we have essentially write after read FIFOs to track false dependencies. We don't want to overwrite data before the consumer has finished consuming it. So we're going to enforce these dependencies using those FIFOs. Now we have a good global view of the design, and as my colleague Thierry pointed out, programming such an architecture is a bit of a challenge because you have to describe essentially those tasks at a high level, but also you have to generate these microkernels that describe things like convolutions or max pooling or batch norm. And this is a pretty big challenge given that you have to take these collection of models. You might want to target different variants of hardware. You might want to provide compatibility with different frameworks. And this is a big engineering challenge. So let's talk about what it means to program this architecture with something like TVM. So to recap the challenges as we step through the architecture, First of all, we have to deal with this idea of tensorization. This tensorization dictates a certain data layout, but also operation ordering. In addition, we have matrix multiply hardware that processes quantized data. And this is a bit of a challenge if you're taking an off-the-shelf pre-trained model. And finally, we have subtle things like memory latency hiding that requires explicit synchronization of tasks. And how do you translate this at a very low level to the programmer who doesn't want to think about hardware, right? So just to give you an idea of how we deal with this, we actually use virtual threads. So Eddie talked about virtual threads being used in GPUs. And this is something that software programmers can understand, right? You have parallel computation, and you need to essentially define thread execution context. You have a loop, you split it, and then you execute this loop in parallel. And so we want to be able to translate that to this low-level pipeline execution that's happening under the hood. And I'm just going to give you a very quick overview of how this gets done. We start with this software-centric view of two threads executing in parallel, right? You have these load and compute operations. You can insert barriers to make sure that these two threads are done before we store the results back to memory. And what happens at TVM, it will insert, the compiler will insert dependence push and pop operations between those tasks. And we also have our JIT runtime that I introduced at the beginning, which handles code generation. And essentially will it will generate a linear instruction stream that sets these dependence flags for each instruction. And finally, you'll see that these dependence flags actually correspond to those FIFOs that I introduced earlier on that essentially allow you to synchronize different modules with one another. And that way we can actually, when we execute our tasks in hardware, we can enforce correct and timely ordering of those tasks. And so I really rushed through this, but what I want you to get is that we can translate a programmer-friendly construct, like everyone has some notion of multi-threaded programming, to something more subtle like pipeline, task-level pipeline parallelism that uses the data flow style synchronization. And this is essentially a cross-stack example of how you can program hardware using TVM. And actually, in our experiments, this leads to much better compute utilization because we are essentially utilizing more resources at the same time. So now I'm going to shift gears to our Colab tutorial. And for that, we're going to have to go back to our website. And I'm going to give a two-part introduction. The first one is how we use TVM to, for instance, massage a schedule to run on VTA, on an accelerator. And then the second one will look at a higher level graph transformations done in Relay to essentially massage the graph so it can, so we can execute this entire compute graph onto VTA. And as you can see, this touches on those two levels of the stack. All right, so I'm going to switch over to our Colab tutorial. So I'm going to open notebook A here that I've already opened. And we're going to run the first cell. So this is just doing the import stuff and just setting up our environment. And so we're just going to look at a very simple matrix multiply. And the reason why I picked this example is this is essentially the Hello World compilation example for VTA. But one of the things to keep in mind is that VTA being a hardware platform that you can actually test and prototype on an FPGA, like this one right here, you might want to target either a simulator that runs on your laptop, or you might want to target actual hardware. And this is defined by this VTA environment. We actually have a file that specifies our target, and by default, it's a simulator. So now that this has been set up, I'm going to import some libraries, but what I'm going to do is I'm going to read the environment target, which says that this is going to run in our fast simulator. Now this is just boilerplate code. If our target were this pink FPGA, we would have essentially reconfigured our runtime on that FPGA board and would have sent a bit stream over the network with an RPC protocol to program that FPGA with VTA. But here, because we're doing things in a simulator, we're just going to run this session locally. We're going to essentially run a simulator on the machine on our cloud instance, actually. And so for this very simple example, I want to do matrix multiplication. But there are subtle things, like initially your data is stored in DRAM, but you have to move it to your FPGA, which has local memory, which is SRAM. And as we've seen before, your FPGA has specialized memories for activations and waits. So essentially, you start with matrix A and matrix B, and you need to copy them over to essentially your input buffer and your wait buffer. Then you need to perform some sort of computation using matrix multiplication on the hardware device, and then you need to store it back to DRAM. And so when we map these to our task level operations, we're doing DMA load, we're doing multiplication, and then a DMA store. So this is pretty straightforward. So first, we're going to look at how we need to write our tensor computation declaration. So Eddie already touched on some points about how we program in TVM. And first, we need to understand is essentially the architecture of our design. And so I inserted some simple prints here that will show us essentially the shape of our different tensor types. So weights are 16 by 16 and our int 8. Our activations are 1 by 16 because here we assume single batch inference. But of course, we could have a 2 by 16 or 2 by 8 input activation. These are int 8. And our output activations are actually int 32 because we're accumulating in a 32-bit register. And in terms of bandwidth requirement, you can see that we need different specialized memories because the throughput requirement changes a lot between those memories on chip. So we're talking about sometimes an order of magnitude between those memories. So that will dictate how many SRAM blocks and read ports you need to have on your architecture. So we're going to start with the tensor computation declaration. So this is something you have already seen in Eddie's tutorial. You start by defining the shape of your input arrays. And then you're going to essentially have those placeholder variables. And here they're essentially four-dimensional because they need to be tiled. And this is one of the subtle differences between your CPU example and your VTA example, because performing computation on a tiled layout already assumes a certain data layout. Next, we're going to have our matrix multiplication declaration. And this is very similar to other examples in TVM, except that now we're performing matrix multiplication over 4 dimensions. There are 2 reduction axes. But other than that, it's pretty vanilla so far. And because this is one of the specificities of our architecture, we do stores in 8 bits, so we can essentially have higher bandwidth. And so we need to cast the data from 32-bit to 8-bit before we send it back to DRAM. This is just a specificity of VTA. Now we're going to move on to more interesting bits, which is, now that you have this tensor computation, how do you schedule it? So in TVM, remember we've borrowed this concept of separation of algorithm definition and schedule from Halide. And so we're going to generate a vanilla schedule here. You can see you have your different buffers. And essentially, you produce buffer A by copying it from your source buffer, your source memory. You produce buffer B, which are your weights. And here, this is where we do our matrix multiplication. So realistically, these loops should be fused into one. And this is what we're going to do with this next step, where we use compute adds. And this is essentially going to nest loops into the main loop that computes the result of the matrix multiplication. I'm going to run this, and here you're going to see how this loop has been massaged. So we used to have 4 loops. Now we have one loop that performs the copying of the activation buffer from DRAM to SRAM, the copying of the wait buffer from DRAM to SRAM, and then the computation using matrix multiplication. And this performs the cast at the end. So this is the more interesting step that requires you to essentially perform some dimensional reordering, because we need to map computation to tensor operations. And if you remember when I listed challenge 1, essentially performing computation on tensorized on the tensorized layout, data layout, requires you to reorder operations. So this is what we do here. We essentially reorder these loops, and we use this really handy tensorized schedule primitives, which essentially maps your innermost loop to tensor operations. So here we're talking about the 3 innermost loops. And now what we also do is that we use, we lower the schedule to VTA intrinsics. And now you see that the schedule looks very different, because now we're calling into essentially VTA high-level intrinsics, like loading a 2D buffer, performing gem operations, matrix multiply operations. This is not very pretty to look at, but if you look at it at home, hopefully you'll be convinced that between this step and that step here, all we're doing is essentially mapping nested loops to VTA hardware intrinsics. And now, running in the simulator, you can actually build this schedule into a deployable module, and finally run it against NumPy to make sure that this is behaving as intended. And here, hopefully, you can check that this schedule that you've compiled and executed on our simulator is running successfully. But maybe you need a little bit more convincing. So we can actually do the exact same notebook, but run it on an FPGA. And what I'll do here is that, remember our target was sim, but what I'm going to change here, and this is on my local machine, but this is exactly the same environment and notebook. So I've changed my target to the pink board. I'm going to SSH into it, and I'm going to launch an RPC server. This essentially listens to incoming connections from my laptop. Okay. So I'm going to launch the exact same notebook on my laptop now. So you should already be familiar with it. I'm going to run everything, and now our target has changed. Instead of running things in the simulator, we're running things in hardware. So as you can see, when I print this, now it points to the pink board. Pardon me? Oh, yes, yeah, thanks. Okay. Right, now things are running in the pink board, and this is all the exact same code. Now it's running in hardware. Of course, the output is going to be the same, but I can actually check what's happening in hardware. And here I've printed, actually, the instruction stream that we're JITting when things are running in hardware. And it's telling us, essentially it's showing us those task level operations. Like we're loading micro-ops from memory, we're performing matrix multiplication, we're loading input and weight matrices from DRAM to SRAM, and we're performing these operations before we store them back. So this is all happening in hardware. Of course, this is a very simple, hello world example. There's a lot more complicated operators, but hopefully this gives you kind of a flavor of how things work at the operator level in TVM. And now I'm going to open another notebook. So this is notebook B. And here we're going to do a little bit more fun stuff. So, people don't really care about matrix multiplication, but they care about, things like puppy classifiers, as Thierry motivated his talk. And so we're going to run a simple ResNet that we're going to get from a gluon model zoo. So this is where things get more interesting, because here we're really leveraging things like relay to perform graph transformations. And I'm going to sprint through a little bit because I'm running short on time. So we're going to initialize this Colab environment. This takes a little longer because we have to install MXNet, since we're getting the pre-trained MXNet models from the model zoo. Okay, it's done. So I'm going to import some packages. Now let's look at our target here. We're running again in the simulator, but now we define this ResNet 18. Essentially, this is gonna define the model that we get from the Gloom model zoo. So this is an off-the-shelf pre-trained model. And again, there's some scaffolding here in case you actually want to target actual hardware. You need to reconfigure the runtime and program the FPGA. But otherwise, we're just running things on the local simulator. And now this is where things get interesting, because we're going to take an off-the-shelf graph. But as I've shown you in the hardware step through, there's a lot of steps that need to go into massaging the graph in Relay so we can run it on hardware. One of the first thing is applying 8-bit quantization, right? Our hardware does not support 32-bit float. This is very expensive on an FPGA to do. So we need to essentially massage the graph to perform 8-bit quantization. I also mentioned to you that because of tensorization, there's a certain way that you need to lay out your data. And this is not always very straightforward to hack, TensorFlow PyTorch to do these layout optimizations. But thankfully, with Relay, we can do this in a single pass. And then we also do have to do things like constant folding to reduce the number of operators. And so I'm going to show you how we do this very quickly. So I'm going to get this Gluon model from the model zoo. And I'm going to use Relay, essentially the translator from MXNet, into a Relay program. And here you can see that the Relay program is something that, Jared walked you through these things. But essentially, you can recognize your ResNet building blocks, right? You have conf2d, batch norm, ReLU. It's pretty straightforward here. But this has to be massaged. And so we're going to do these two steps of quantization and data relayout. And what's nice here is that we have passes that we can just call, and it will do this for us. So I'm going to apply these two passes, and then we're going to look at the IR. So the IR is not going to be very pretty to look at, but I just want to catch your attention on a couple things. So for instance, if you look at this conf2d here, we've modified a few things, or maybe here. So we've modified a few things. The first thing is that the data layout is not NCHW anymore. It's actually tiled. So it's NCHW, small n, small c. So now we go from a 4-dimensional to 6-dimensional tensor. And this is important for us to do in order to feed the data to a tensor processor. But also, now we are using int32 because that's our accumulator output data, int32 instead of floating point. And you can also see that, for instance, your output activation is cast at 8-bit in. So this gets massaged, and now we can actually perform compilation of this entire model. And for every conf2d or fused operation, we're essentially calling into a TOPI operator, which Eddie has already talked about. So this is going to run. And now we're going to perform the inference. Again, this is running in the simulator. But I'd like to convince you that this can also run in hardware. So this inference latency is actually measuring the simulator inference latency, which is running on a virtual CPU. So it actually doesn't really tell us anything about performance, but at least it gives you some assertion that the compiler transformations we're doing are correct. And now if I were to switch back to my own notebook that is now connected to my Pink FPGA, I can rerun the exact same tutorial. This is the same source. But now I'm running things on the Pink FPGA. And so this is going to take a few seconds to compile the graph and import all the libraries. As you can see here, our target is Pink because we changed that in the config file, so we're not running this in sim anymore. see. So you can't have a successful FPGA demo without something kind of hanging or crashing. So we're going to try to do this again. All right. So let's try. I'm going to restart the RPC server. Okay. Sorry about that. And so while I just run this, I'm going to wrap up to give enough time for my colleague Luis to give the next talk. So let's take a look at the final output. So we perform the inference here on this ResNet image, on this ImageNet sample. So here you can see that the gap has been lessened on this FPGA. And also what's really neat, and because of the enlarged font, the layout is a little bit messed up here, but what's really nice is that you can look at each operator thanks to our debug graph runtime and see how much time, how many milliseconds we spent in each one of those operations. So this is a really handful way to essentially look at the performance of this, here we're using a toy FPGA, but this is something that we use in a lot of classes. And you can essentially get a breakdown of where you're spending all the time. All right, so that concludes the tutorial part. I wanted to point out that essentially we've addressed some of these challenges by looking at scheduling primitives that we can perform in TVM. Like how do we lower algorithms to tensorization intrinsic? How do we hide memory access latency? But also we've shown how we can massage the graph in Relay, like to perform data layout transformations, which are really useful to us. And I also wanted to touch on some more exciting things that you can do with VTA very quickly, because now you have control over the compiler and hardware stack. You can do a lot of fun co-design experiments. So VTA is this modular deep learning architecture template. You can modify your tensor intrinsic, your data type, your memory subsystem, as well as your operational coverage. And that means that you can essentially perform hardware design space exploration. You can perform knob exploration, circuit exploration. Essentially, by constraining this problem to a given FPGA and a given model, you can get a set of VTA hardware candidates that all operate at different, let's say, have different theoretical throughputs. But you can also look at how much actual throughput you can gain out of these different hardware candidates by performing auto-tuning with auto TVM. And that way, you can essentially perform auto-tuning on your hardware candidates and deploy a highly tailored both hardware and software stack onto your FPGA, which is really nice. So this is essentially an example of a hardware-software co-design. And we have a paper that's under review that discusses this. And in terms of end-to-end performance, we did some experiment on edge platforms. And we could see that, for instance, moving from an ARM Cortex CPU to a Mali GPU to an off-the-shelf Ultra 96 FPGA board, it's also based on the same ARM SoC. We could actually target some very interesting workloads like DC-GAN that does RL exploration for AIs playing Atari games. And what's nice here is that you can see that the Mali bar is missing, and it's because at the time of the experiment, ARM-CL actually didn't support some of the operators we needed to run DC-GAN. So you can sort of stay ahead of the curve on novel models using TVM. So that will conclude my section of the talk. I won't take questions right now because I'd like to give my colleague enough time. So I'll take your questions over lunch. Thank you all.